Hello, everybody. In this video, we're going to talk about algorithmic fairness, and we're talking about it as an example of the way the computational lens can impact other areas of study, and specifically in the way that theory and computer science in general can help address societal concerns of computations. And we'll talk about it later. This is a very active research area. The results I'm going to talk about today in this video are a few years old. Perhaps by the time people watch this video, there will be older and outdated. And that's absolutely fine because the point that I'm giving, and it's only going to be kind of a taste, is not this particular result, but a few messages that I'm going to perhaps discuss a bit later at the end of this video. And I think these messages will always be true. So algorithms make and inform decisions, and it's more and more decisions. I like this cartoon from the New York Times, I think, that one of my students found. They help us decide, or they have a huge impact on who we date, what ads we see, what movies we see, what's the credit card rates that we get, and even in other very dramatic notions of whether we are going to be set on bail or held until our trial. So algorithms are making very important decisions, or at least inform very major decisions, and this kind of creates a huge amount of questions that fall into this interplay between computation and society. So more and more policy questions revolve around computation. And to name a few things that came up in the last few years very strongly, and there are more, we can talk about fairness, discrimination. This has been in the news a lot for good reasons. Privacy. All of these algorithms rely on a lot of sensitive information. Is our privacy preserved? Censorship versus free speech on social platforms, a huge area. I'm recording this video a little bit more than a week before the 2020 elections, a very big deal in this election. Filtering the news in general, the filtered bubble. You see, you search on Google or you see your Facebook feed. What kind of things are you exposed to? Are you exposed only to what we think is your opinion already? Identifying fake news, again, a huge issue in this election. Net neutrality was another issue. National security versus individual freedoms. There was an issue with a cell phone, whether a company needs to allow the government to break into this cell phone, perhaps in a national security event. And a major issue for future years is loss of jobs due to automatization. And we expect it to be major. One example is this idea of automated cars that would potentially get rid of a huge amount of jobs of drivers. And we need to take all of this into account. And when I say we, I'm saying we as a society needs to address all of those. And policymakers need to make decisions. And the question is, okay, these are all dilemmas. Perhaps computer science help develop these issues, but what should we do as computer scientists about it? Finally, another example is the fear of AI. Is AI is going to take over? And CS, computer science, cannot make these decisions. We cannot have a paper saying, you know what, this is how you solve privacy. This is how you solve fairness. This is the right thing with respect to net neutrality. This is not up to us. This is up to society. It's about norms. It's about the context. There is no single mathematical solution to any of these issues and any other issue that would come up in the future. But we can inform the debate. Because this debate relies on a lot of technical issues, we can inform them, and we can also extend the range of solutions. So for example, in privacy, if the issue is, are you allowed to conduct some research on a very sensitive database of individual data, then if in the past the question was, okay, either do this research or don't do it, perhaps with computer science we found ways of getting ways to do it and still preserving some levels of privacy, and it is up to society to decide now if these levels of privacy are sufficient. So one of the things I want to tell you as newcomers to computer science is that this is on us. We are part of the problem and we need to be part of the solution. The specific example we'll discuss here, and we could have discussed any of the other things, and all of them have some theory or could have some theory perspective to them, that this is discrimination. It's not a coincidence. This is currently one of the main focuses of my research. So population includes various minorities, for example, based on ethnicity, religion, medical factors, geographic factors, and these are protected either by law, by policy, and sometimes just by ethics. So the question is, would algorithms discriminate or make more equitable decisions? So perhaps we think, oh, algorithms are these objective creatures, and instead of humans that are biased and subjective, let's give algorithms a chance to clear our world from discrimination. This is a beautiful idea, but currently it doesn't seem that that's the situation. We see more and more examples where if you leave algorithms to their own devices, they can propagate and even amplify biases. So it's not enough to learn or optimize. It's not enough to say, oh, this algorithm is based on machine learning, and machine learning just want to optimize. It has no other desire, and therefore it will be fair. That's not the case. It's not even the case that once you have a representative set of data, then everything will be okay because you learn from this data. It's pretty complicated. It's not easy to address discrimination or even to understand what discrimination is. So what is the role of CS in this specific case and of other neighboring areas like statistics? So fairness is multidisciplinary. Philosophy, law, economics, statistics, social sciences, many of them were way ahead of computer science to the game. Even before there was computer science, they still discussed these issues of fairness. But there is a lot of interest in computer science in recent years, let's say the last decade, from the time I'm recording this. This is still quite young within computer science. So what would computer scientists do? As I said, we are part of the problem. We have to be part of the solution, because this is the kind of huge scale that none of these other disciplines have been looking into 30 years ago. It was just not in their mind, because it wasn't a realistic scenario. And we have the tools to address one of the part of it is computation. So we need to be part of it. And one of the things we can do is provide models, which is what this class is talking about a lot, definitions, algorithms. And in this, we are following examples from other areas like cryptography, like privacy, that again, at the beginning were very loose, but with the work of theory have become very deep and give a lot of understanding. So we want to give a language, a computational language to address, to discuss, to argue issues of discrimination. And we need a multidisciplinary village. It's not enough for computer scientists to do their thing and solve it, but it's also not enough to just wait for other disciplines to do their things and we will just implement. It doesn't work this way. We need a bridge between the normative aspirations of some of the other fields and the computational realities that we understand a bit better. But once you try to collaborate with other areas, there is a language gap and there is also a value gap. So different fields have different values, things that they cherish. And that's something that we need to deal with. It's hard, but it's harder to ignore it. Search for this quote. So the theory of algorithmic fairness, it played a major role in the last decade that turned this area into a very vibrant area. And yeah, there were also, even before the last decade, topics that relate to fairness in computer science, but I'm talking about kind of this version that is more related to the growth of machine learning. And it's growing in sophistication and depth. So I cannot show you some of the major results that we have because they are beyond the scope of this course. But I will show you something just to give you a taste and to show you that what we learned in this class is very relevant to anything we want to address using computation. So the research that we uncover relates to machine learning, optimization, privacy, complexity theory, which will demonstrate cryptography, computational social science, game theory, and more. We need everything we know to address this problem that is pretty difficult. It's very dynamic, and again, I don't expect what I'm telling you now to be the way I would have presented it if I record it in 5 years. But the message, I hope, would be still relevant. Right, so by the time you watch this video, assuming that these videos will have some longevity, it may be out of date. So let me give you a little bit of a taste of what's the issue here. So individual probabilities. What do individual probabilities mean? So you go to the doctor and they tell you, you have this probability of developing diabetes in the next 10 years. What this probability means? Probability over what? I'm a single person. I'm not an experiment that you can run many times and in 20% of the time I develop diabetes and 80% not. So what does these numbers come from? They try to capture some kind of randomness in the environment. some of the things around us may affect us, and they seem to be random. What is this randomness in the environment? It's not really randomness. We're not talking about quantum effect. We're talking about limited information. We don't know everything, or the physician doesn't know everything about me and cannot predict all the things that may affect me. Will I have a job or lose a job? What kind of other struggles I'll go through my life? Are there environmental effects? Very many things that are beyond our information, and we try to capture with this notion of randomness. In addition, we have bounded computational resources. So even if I gave you everything about the world, you cannot really calculate it, you cannot really run it and simulate it. So we have limited information, bounded computational resources, and this gives us some notion of probability, or at least intuitively it should. What does it mean? This has been debated within statistics for many years. I'm not going to resolve it here, but I want to show you a little bit of its challenges. So this is this individual going to the physician. The physician tells you 40% you develop diabetes. You ask them, okay, what does it mean? Where does this 40% come from? Tell you, no, there is this study, and the study corresponds to people like you. Your data is consistent with this study, and 40% of this individual develop diabetes. So you go home and you find a different study, again, capturing people like you, but perhaps with different attributes, still your attributes, and then there are 70% probability. Does it mean that you now need to be much more worried? Is it 40%? Is it 70%? Both of these studies capture your data, but perhaps capture some other populations. What about you? And even if you find a different study that says 40%, does it mean that this confirmed the 40%? Or perhaps now you should be even more worried because there is this, you have this risk factor that gives you 40% and this risk factor that gives you 40%. So perhaps your individual probability is even higher. And in fact, even if you find a study that doesn't capture your data, but captures some other people's data within the first study, and this is 70%, what does it tell you about you? Perhaps this 70% is one of the reasons for the 40%. So this population perhaps is contributing a lot and your probability is lower. How do you make sense of all of these probabilities? So in fact, you cannot really, you don't have enough information to know exactly what is your probability. And in a sense, there isn't really a clear meaning of what is your probability. And that's the debate within statistics that I refer to. But perhaps even if I can't tell you exactly individually, what about fairness? So you cannot expect to have a correctness, but perhaps you can have fairness. So perhaps assume that these predictions of probabilities are for the sake of estimating life insurance rates. How do you make sure that the predictions are not consistently higher for some subpopulation, making their insurance rate higher? So even if we don't know individually, can you make sure that there is some fairness in these decisions? And we cannot expect a single definition of fairness here and in any other setting, because fairness is context dependent. In different contexts, in different community, it will mean different things, and it incorporates social norms. There isn't a single definition of fairness. They wouldn't be, but we want to develop a rich possibilities of definitions so policymakers can debate and choose what makes sense for them. And in fact, discrimination is subtle. This is a game I've been playing for a decade at least. of finding ways of abusing definitions of fairness. Each one of those can be abused. You can discriminate even that you satisfy a particular definition. And you can discriminate in very subtle ways. You don't even know it when you see it. There are cases that the community has looked at, and there was a debate. Is it fair? Isn't it fair? There is some argument that perhaps it's not a discrimination, some argument that it is a discrimination. So it's not something objective, it's something that depends on your social norms. But still, definitions are extremely important because without definitions, you can say, okay, here is my algorithm for determining these probabilities. And let's argue, is it fair or isn't it fair? So then I need to argue about a system. I need to understand your system. It is much better that we argue about definitions. And once we have a definition, then we enforce the system to satisfy the definition. And in this, we follow this example of cryptography, privacy, game theory, where very complicated things have been developed into definitions, a variety of definitions where we understand the interplay between these definitions and we can obtain them. And this is an important language, just like the language of philosophy is important to understand fairness, just like the language of law is important, the language of statistics, the language of computation is important as well to understand fairness. And I want to get into a couple of technical slides just to give you a sense. It won't do much, but to show you that what kind of things does computation bring into the table. So group notions of fairness are the most prevailing notions of fairness. They're very weak, but still. So what they mean is that for a few protected groups, S, for example, a group based on some ethnicity, what you want to say is that your system, your algorithm treats S similarly as it treats the general population U. What does it mean to treat similarly? There could be various things. For example, we have this notion of statistical parity. So let's say you want to predict or perhaps to classify. Let's say you want to decide who is accepted to a college. Statistical parity means that you accept the same fraction of candidates from S as you accept for candidates from U. We have balance that talks about false positives, false negatives, and they equalize that. You have notions of calibration that talks about accuracy, and then you have more, and definitely I don't want to get into all of this. It's way beyond the scope of this course. All of these notions are very easy to work with, but provide very weak protection. They're very easy to abuse. And I'll give you an example soon. In fact, they can even cause more harm than good. They are at odds with each other. These were some results that created some panic. You cannot get all of them together. They are inconsistent with each other. And they also hurt utility. And finally, there is a more philosophic question, which is very important, which is which sets S you want to protect, which sets S deserve to be protected, and who decides which are the sets that need to be protected. And it turns out that sets that need protections don't even always know it themselves. So groups that are oppressed do not always understand that they are oppressed in real time. Sometimes they internalize this oppression and they don't feel that they deserve protection. So it's completely unclear what sets to protect. This is where finally we're going to look at the computational perspective, the computational lens, and with just a single example. So often the weakness of group notions of fairness is that they don't protect important subgroups. Let me give you an example. Let's say that you are advertising a burger joint in some social media, but this is targeted advertising, and you target vegetarians from the group S and the carnivores from the general population. So even though perhaps you have statistical parity because you're advertising for people from S a lot, you may be excluding people from S because you're advertising to the wrong people. You're advertising your burger joint to vegetarians from this S that you want to protect. They will not come to your burger joint. They are vegetarians. So it's true that you advertised a lot to S, but you deliberately excluded the right subpopulation of S, which are actually the carnivores of S. A different example is to treat all loans applications from S as equally qualified. Instead of saying, okay, this individual would repay a loan with very high probability, this other individual would not repay a loan with high probability, just give the average. A random person from S would repay a loan with probability 70%. Perhaps 70% is too low to give a loan. Now nobody gets, although there are some qualified applicants. So fairness relies on identifying subgroups that are relevant to the task at hand, like the carnivores of S or the qualified loan applicants. But there is no literature that tells you to protect carnivores from S. There's no population in the world where somebody say, the carnivores deserve your protection, or even the qualified loan applicants. So this again comes to the question of which groups to protect. It's completely unclear. And here come computer science, theory of computer science, with a sequence of new definitions that take these old definitions, these group notions, and take them much further. These are multi-group fairness notions, and they offer fairness protection to every large group that can be identified given the data and given the computational limitations. So to answer the question which group to protect every group that you can identify. So for example, if your computational power is quadratic algorithms, identify every group where you can protect every group that you can identify its members with algorithms that runs in time, which is quadratic. And of course, there are other, perhaps more natural definitions of groups than quadratic algorithms, but I'm using what we learned in this class. So this is, in a sense, the best possible. If you can't identify a group, you cannot protect it. I cannot make sure that you're advertising to the right people if I don't know, if I can't even identify people that are right. And this is a computational perspective to fairness. This goes much beyond that. And in general, a computational perspective in all of these questions is about understanding that the different entities in all of these games, in all of these scenarios, are all computationally bounded. So the algorithm that learns a predictor or a classifier is computationally bounded. The algorithm that audits, that tries to tell you this is fair, this is not fair, is also computationally bounded. All of these entities are computationally bounded, and we need to take it into account in our definitions. And taking into account in our definitions create a completely new set of definitions. So this was, again, only a taste. I don't expect you to understand all the technical issues, but I hope you get some of the messages, so let me talk about that. So first, the societal impact of computation is on all of us. We cannot say, oh, this is something for philosophers. This is something for social scientists, for lawyers, for legal experts, for statisticians. No, it is on all of us. It is on all computer scientists, and different sub disciplines of computer science are all taking a close look into the societal impact of computation, definitely machine learning and AI, but other areas like HCI and others are all looking into fairness, into other considerations of computation and society. It is on us, it is our responsibility. And in addition, our tools are very useful for that. So we cannot address these issues alone as computer scientists and definitely as a theoretician, but this cannot be addressed without us. And the computational perspective is very powerful because we need to account for the computational limitations of all parties. So what we learned in this class, of course, is not necessarily enough. And that's why we have subsequent classes, which I hope you will take. But what we learn is very useful for this and many others questions about computation and society. Thank you.